Yes, so that's well known that varieties of universal algebra, which is the same thing as categories of algebras of Lobby theories, correspond to finitary monads on set. Finitary means monads preserving filtered coordinates. So this is old fact due to Linton in 1965. So Lobby theories deal with X, Y array operations, which are interpreted as mappings, A to X to A to Y, where A is a set, and traditionally, in the language of traditional algebra, these are Y tuples of X array operations. Which in fact makes possible to replace substitution of operation by composition of these X, Y array operations. Because if you have an array operation and you have n tuple of an operation, so you make it as this n tuple and it's just to compose. And Linton, a little bit later, he showed that algebras for every monad on set are described by equations between such operations. So now these arities are arbitrary sets. And in particular, this is not in Linton, but in particular, lambda monads, which means monads preserving lambda filtered coordinates, correspond to lambda equational theories, which mean that X and Y are lambda presentable in sets. Of course, it means that they have cardinality smaller than lambda. So this is just recollection of well-known things. And the reason why this Linton result is true is that X, Y array operations corresponds to morphisms between free algebras from F to Y to F to X. And free algebras are dense in algebras. So in some sense, this is the reason why this Linton result works. Then motivated by Linton, I introduced the following concept quite some time ago. So now K is a category. Now a type over K is a class equipped with mappings T from this class to pairs of objects. In fact, this how to say this gives these arities of operations. So in some sense, this omega is the collection of operations. Each operation is equipped with arities. So these are two arities, X and Y. And one assumes that you have only a set of X, Y array operations. So this, in this terminology, free images are sets. So it's just formalization of the fact that you have sets of X, Y array operations, or more precisely of Xi array operation symbols of that type. And just these arities are not objects of real category. Like if you are on sets, so these are these usual arities, which are sets. So then the definition of a term is quite clear. So every operation is a term. The arity is given by this T. Then every morphism from X to Y determines, from Y to X determines XY array term itself. Just immediately will be seen why it changes here when I will come to interpretation. Then two term compose, so XY and YZ array compose to XZ array term. Then this assignment X, which sends terms to operations, again is functorial. So X of GF is XG XF. And also the composition of terms is associative. So this is definition of a type and of terms. Now equations are pair of terms. an equation theory, a class of equations. So in some sense, this definition is exactly tailored for the situation Linton used. And one should now add that this A to X now denotes the set of morphisms from X to A. It is at X, it's contravariant. So this is the reason why one changes here these sides. Morphism goes to XY array term. And I use notation. What does it mean? A to F and H to X. I will not need it, in fact, too much, yes. To finish this, so now it's an algebra of type. So it's an object of K, which is equidistant mappings from X to A to Y to A. So this for every XY operation symbol. And now terms are interpreted in that way that XF interprets as A to F, and the composition interprets as a composition. And now algebra satisfies equation if these are the same for this algebra, and theories satisfy, algebra satisfies the theory that satisfies all equations of the theory. So this is just, so what's the point of it? That in some sense now we take as arities objects of our category, and then it's in the same way as I indicated below in sets. Homomorphic algebras are again clear, so that simply it commutes. And notation, the category of algebras for theory E and forgetful functor 2K. I will give you examples soon. So just I have to say that this is my original definition of terms. It didn't contain this condition 5, but it doesn't change interpretation because this composition is always valid in any algebra because this is given by actual composition. So it doesn't change the strength of the situation. So it doesn't change the interpretation of terms on algebras. So I added it because my equation of theories and algebras coincide with pre-theories and algebras in the sense of a recent paper of John and Richard Garner, which is in some sense, I think this is, I will give you, a little later, I will give you, say, the historical recapitulation of things. But for them, you see here, one has this theory, say, which is, in fact, the omega is a category because you can compose things. The composition is associative. It's equipped with a functor from the category K to that given by this X. And this is, in fact, their definition then. So how this situation could naturally appear? So you have a concrete category over K. So you have a sole functor from A to K. And you define that for any xy, this omega x, this list of operation symbols, consists of natural transformations from ux to uy, where ux denotes the set of mappings from x to u of u objects. But just here, these omegas don't need to be sets because you can have a class of natural transformations. So the resulting type, it's in parentheses now, it's not legitimate. But ignoring this, we get terms again and where x to f is u to f. And this is the composition of natural transformations. So it gives not legitimate equation of theory and forgetful functor, such that this image is done by components of natural transformations. This is in fact the main idea of Rovere, that operations in fact are natural transformations. So that from any faithful functor, one gets a type and one gets a theory, but somewhat one has to forget these legitimacy things. It will not happen it does, but originally that played a role in what I wrote, because just I will tell you at the moment, yes, so just after this. So if U has a left adjoint, so the natural transformations from UX to UI correspond to natural transformation of AFX to AFY. So it corresponds to morphism from AX to AY. So in this case, one gets a real type, legitimate, and a theory. But if U doesn't have an adjoint, so you can have something which is not legitimate. Still, of course, you can look at algebras, because, for instance, there are situations, if you take, say, complete lattices over sets, so you don't have an adjoint, but still it's given by equational theory, but you meet this non-legitimacy. And another situation where it appears if you work over finite sets, so your algebras are finite. So then, for instance, if you have just one unit operation, so you don't have free algebras in finite sets, because free algebra over one element is infinite. And then in this situation, you can have natural transformations which are not defined by operations, which are not defined by terms. For instance, this example is unary algebras, finite algebras. If you have finite algebra, you take an element and you follow the operation. So at some moment you come to fixed point, because you have only finite number of elements. So then you take as operation that an image of this element is this fixed point. So then this is an example of a unary operation which is not given by a term. And these things are important from Jan Reiterman in his Birkhoff theorem of finite algebras, so these implicit operations. But it doesn't, just I want to explain somewhat one of motivation for this definition. But now it doesn't play a role here, so you always have here the algebras. So this is, as I told you, it goes to Linton. Due to Linton goes back to Lovier. And as I told you, Linton showed that U is monadic. If it's monadic, then this comparison factor from the category of algebras for the monad, and this induced equational theory is an equivalence. And given T algebras of elements from A to X correspond to morphisms from X to A. So this is the situation in a general category. Now, let us now add that our category is locally lambda presentable. So then we say that type is lambda array if arities are lambda presentable, and theory is lambda array if type is lambda array. So in the terminology of this Burg-Gardner paper, our lambda array theories coincide with K lambda pre-theories, where K lambda denotes the representative small subcategory consisting of lambda zero objects. So I started with the fact that finitary monads in sets correspond to Lovier theories. So now this is true in general, that lambda monads on K correspond to lambda theories over K. You see, this is one goes from set, in fact, to any locally unrepresentable category. Yes. So there are now two possible reductions. So the first reduction is that still you have lambda theory over local representable category, and now you have a dense subcategory consisting of lambda objects, but not all, maybe something smaller. So then you take a subtheory where you take only those operations whose arity y belongs to A. And then since it is dense, then the reduct factor, one can show this reduct factor is an equivalence. So again, this is also that paper of John and Richard, that somewhat you can reduce say, the complex of operations if you come down to a dense subcategory. That's another reduction. If lambda prime is smaller than lambda, so let us say that type is lambda prime lambda array if arities y are, sorry, that's here a mistake, are lambda prime presentable and arities are lambda presentable. So this means that we limit arities of x by lambda prime and arities of y by lambda. And then again, monads given by such thing on a local lambda category preserves not only lambda filtered coordinates, but lambda prime filtered coordinates. Yes, so you can go down with this preservation. Good. So these are some kind of additions to this following, to this basic thing, that you can make some reduction on both sides of arities. Now, let's come to some examples. So let's take the category of posets and monotone mappings, which is locally finitely presentable. So finitary monads on posets correspond to finitary equational theories. But now, one element and two element chains, there are dense in posets, so it means that it suffices to take only x1 and x2 operations. You can reduce arities of y. So what is the first? These are the usual x-array operations. And what is the second, in fact? So it is now it's important now to understand this. So it is a two-tuple of x-array operations. Yes, because it's two, it's a two-tuple. But not all two-tuples, because this is a chain. So these are two tuples fg such that f is all equal to g. So in fact, this somewhat expresses inequation between x-array operations. Yes, so by operations of that kind, you can express inequalities between usual terms. And the consequence is that finite monads on posets corresponds to finitary inequational theories, which was shown in a recent paper of Adamek, Ford, Milius, and Schroeder by the end of last year. Another example of this situation, of this, how to say, this reduction here. So let's take simplicial sets, which is locally finitely presentable category. So again, finitary monads corresponds to finitary equational theories. Now, simplices are dense. So it means that it's sufficient to take only operations having as arity, second arity as simplex. So delta 0 is just 1, so these are usual x-array operations. But now, what happens if you take as this arity delta 1? It means, say, one simplex, it means an edge. So you get a mapping from A to X to A to delta 1, which corresponds to mapping from delta 1 cross A to X to A. So in fact, this thing captures homotopy between two operations. So like here, this two-element chain captured inequality between operations. So here, this delta 1 captures homotopy between two operations. In that way, you can say equationally that two operations are homotopic. So for instance, if you have homotopy monoids, which means that you take associative only up to homotopy, so this is given by equational theory or simplicial sets. That is homotopy expressed by using delta 1. I think this example has quite some potential because, of course, you can also take other simplices, which would mean that you get higher homotopies. On the other hand, that's another approach to homotopy algebras, which goes back to Badziok, Bergner, and I also wrote a paper about that, is that you have a Lobby theory of simplicial sets, which means usual models are finite product preserving functors to simplicial sets. But now you change it and you take only functors which preserves finite products up to homotopy. and then we have homotopy algebras. But this is certainly more general than these things, because I don't think that these homotopy algebras given by present version of products up to homotopy are captured by real monads, or by algebras for real monads. Probably one has to take homotopy algebras for something. But for some good special cases of these homotopy structures, you can do it by an equational theory using this. You see, all the time one is using this idea that you work with X, Y array operations, which looks quite natural if you do it in sets. Another example. So now let's take the category of metric spaces, and I allow distances infinity, so these are generalized. And as morphisms are non-expanding maps, it means that these maps cannot increase distances. So this category is locally L1 presentable. That wouldn't be true without distance infinity, because you wouldn't have products, for instance, or coproducts and so on. So this is a category now which is not so nice. It's only locally L1 presentable, because L1 presentable objects are those having cardinality smaller or equal to 0, so having cardinality either finite or countable. And now again, L1 array monads on, that's something missing, it should be on metric spaces, correspond to L1 array equational theories. And now here, what's dense in metric spaces is 1 and 2 epsilon, where epsilon means the space with 2 points having distance epsilon. So this somewhat substitutes this 2-element chain from both sets. And then it is again dense, because any metric space can be obtained by a colimit of these giving points and by giving distance between points. So now what does it mean that you have a x to epsilon array operation? So again, you have, like in both sets, you have 2 x array operations, but now they have distance small or equal to epsilon. So you see, in the situation with both sets, you could express in equations. In a situation with simplicial sets, you could express homotopies. Here you can express the fact that 2 operations are of distance small or equal to epsilon. And these metric equations were used precisely for the first time by Weaver in 1995. So again, this technology shows you how you can equationally describe things given by metric equations. Now the problem is that you cannot express finiteness in metric spaces using finitely presentable objects. But you can use what Ivan told us in one of the seminars of the last fall, that metric spaces is isometry locally finitely generated. And finitely generated metric spaces are precisely finite metric spaces. So you have a concept of finiteness for metric spaces, which gives what you want. It means finite metric spaces, which is given categorically, but you need isometries for phrasing this. So you need a factorization system of metric spaces consisting of isometry and consisting of surjective and isometry. And now one can try to adapt the previous things to that situation. So now one can change the over category, which is not locally lambda presentable, but again, another mistake, it should be lambda generated here, yes. So now you are in a category which is, this M plays the role of isometries. This is the class of morphisms. So in general, you have a class M here. Locally are now lambda generated. So then we change definition of a type that it's lambda array if arities of x and y are lambda generated with respect to n. So now over metric spaces, those finitely series in this sense would be that having finite arities. And I have to add that every category which is M locally generated is locally mu presentable for some mu, but not for the lambda. So like in metric spaces, it's locally finitely generated, but only locally RF1 presentable. So still one has all these concepts for presentability, but then one can go down in some sense when it is locally undergenerated. And one can again prove the similar theorems as we had for lambda presentable categories. So if K is M locally lambda generated, and at the same time locally mu presentable, and if E is lambda equational theory, in that sense, it means arities are lambda generated, then the category algebra is monadic. And in the induced monad is mu array, so it preserves mu directed colimits, but it has another property that it sends lambda directed colimits of M-morphisms to lambda directed colimits. I don't want to say that it preserves lambda directed colimits of M-morphisms because it has in fact a dubious meaning. So I mean that one, that it sends lambda directed colimits of M-morphisms to lambda directed colimits. So in the case of metric spaces, it sends lambda directed colimits of isometries to lambda directed colimits. Because in general, that example for that, such monad don't need to preserve M-morphisms. So for metric spaces, such monad don't need to preserve isometries. But if M monad is good, so still the category is still M locally undergenerated and locally presentable. And now we have again mu array monad, which preserves M-morphisms and lambda colimits of them. So it's more special than that one in the first theorem. So then it's given by lambda equational theory. Such that the category algebra for the monad and its algebra equivalent. So this is another possible equivalence between, say, lambda monads and lambda equational theories, which works over categories which are not locally lambda presentable, but only locally lambda generated. But the situation is not perfect here because I cannot say more. So I know that any theory gives monad, but I don't need that this is such good monad that it works back. So now let's look what does it mean for metric spaces. So to be finitely equational over metric spaces, so it means that operations have finite metric spaces arities. We know that the corresponding monad preserves our R1 colimits, and it sends directly colimits of isometries to colimits. And conversely, the monad even preserves R1 colimits and isometries and sends the colimits to the colimits of isometry colimits. So then it is given by finite equational theory. But monads given by those theories don't need to preserve isometries. So you see the situation over metric spaces is much less clear than over posets, because just due to the fact that this category is not so nice because it's not locally finitely presentable. But this is what I can say about these. So now if the metric space is discrete, what does it mean to be discrete? It means that distinct points have distance infinity. So then the topology is discrete topology. So such spaces are, so now I'm using terminology which we used in our book with Ilka Adamek and Enrico Vitale, is perfectly presentable, which means that its home functor preserves shifted colimits. Maybe you have to recall what does it mean shifted colimits. So shifted, like filtered colimits in sets, are those which commute with finite limits. So shifted colimits are those which commute with finite products. So filtered coordinates, they belong to the doctrine of finite limits. Shifted coordinates belong to the doctrine of finite products. And over sets, they reduce to filtered coordinates and reflexive co-equalizers. So, but the consequence is that monads for metric algebras of this Beaver paper preserve shifted coordinates because in that situation, the arities of operations are discrete, maybe I should find it here. Yes, so here in this paper, one uses situation where operations are just usual operations. They are not metric. But one uses these equations, which means that in fact one takes as x, one takes discrete spaces, and as y, one takes also these two epsilons. So then by this reduction I mentioned before in lemma 1, one can make this reduction here if it is discrete. So in some sense, preservation strengthens to preserve properties which are preserved by discrete things, and these are shifted coordinates, because finite discrete spaces have the property that this A2X preserves shifted coordinates, so it preserves filtered co-equalizers. So these monads then preserve shifted coordinates. But you can get such monads or metric spaces which preserve shifted coordinates also by other way, because you can take, in fact, any monad which is induced by an operand. So it means that instead of Cartesian product for making operations, you use tensor product for making operations. You can do it because metric spaces are symmetric monoidal closed, where tensor product is, Cartesian product is plus metric. For instance, then the monad for monoids, this is an example of a monad given by such thing, has such operation. And similarly, you can take monad for generalized norm spaces. Generalized again means that you accept norms equal to infinity. So which are monoids, which are equipped with unary operations. And this key condition which you have for norm spaces follows from the fact that plus is non-expanding, because plus is the norm of x plus y is more equal to that thing, because the norm is given by this plus operation. So you can get many other examples of such monads or metric spaces which preserve shifted coordinates, and I don't think that these monads are given by finite equational theories. I don't believe it. I don't have a proof. I don't believe it. Another example, you take unit ball from Banach spaces to metric spaces, and again the corresponding monad preserves one filtered coordinates. It's monadic that I showed last year, but it doesn't send the coordinates of isometric spherical coordinates. So this monad doesn't have this good property that as those given in local, this isometry locally generated category. So it doesn't send directed coordinates of isometric directed coordinates. So this is another example of monads or metric spaces, which good. Now I spent a quite a lot of time in this unenriched situation, but everything can be enriched. So now we have a symmetric monoidal closed category D, you have D category, and now this A2X means the D object. So this A2X is not a set now, but it's the object of D. And we can immediately define enriched equational theories, and then they correspond to enriched pre-theories of Burke, Garner. And if V is locally lambda presentable as a closed category, and K is locally lambda presentable D category, then that paper shows that enriched lambda equational theories over K correspond to enriched lambda monads on K. You see this result just, and now I want to give you a kind of history of this result, because Lincoln, it means that monads corresponds to this XY array operation, was enriched by Dubuc in 1970. Much later, John Power enriched this older Lincoln. This older Lincoln says that finitary monads on sets correspond to Lovi series. So he enriched that and showed that enriched finitary monads on a symmetric model closed locally representable the corresponding Lovi series. But now he replaces finite products by finite cotensors. And then John Paulis Nishizawa, a little bit later, did the same for any locally finitely presentable V category. But the Lovi series were not comfortable. So only that paper, I see this fundamental paper of John and Gardner, made the final step, just showing that enriched lambda series over K corresponds to enriched lambda on K. Now again, coming back to examples. So by post sets, now what changes now? Now these things are post sets and not only sets. So now this mapping is a monotone. So it means that operations are monotone. So you not only use order to restrict this arity in A and this n-tuples on A, but you also need a things are monotone. And in that mentioned paper of Adam and Ford, Milius, Schroeder, they did also this enriched case, and they call this as coherent. So coherent means these operations are monotone. And they show that enriched finite monads over post sets correspond to inequational theories for coherent algebras. So again, it follows from this general situation. Now, over metric spaces, these operations are non-expanding. And in the special case where X is finite and discrete, and Y is finite, so they correspond to theories considered by Mardar, Panangan, and Plotkin, and they call it finitely unconditional equational theories for quantitative algebras. And they are motivated, that's very interesting, very important paper, motivated by probabilistic computation to introduce these things. So it can be phrased in that enriched approach, general enriched approach. Taking metric spaces, so metric spaces are isometry that should be missing something. Isometry locally generated as a closed category. So now, again, what we did with Ivan, it can be done enriched. So in fact, it's enriched isometry locally finitely generated with the tensor unit finitely generated and tensor product of two finitely generated is finitely generated. So this is the definition to be isometry locally finitely generated as a closed category. Like in for local categories, it means that tensor unit is finitely generated and the tensor product of two finitely generated is finitely generated. So then these theorems 1 and 2 I showed you about locally generated can be made enriched, and we get connection between finitely enriched monadometric spaces and finitely enriched equational theories over metric spaces. No, now, but again, also, of course, in this enriched case, the situation is also not completely described like in unenriched case for metric space. So, as I told you, shifted colimits are those which commute in sets with finite products. One can show that also there are those which commute with finite products in metric spaces. So shifted over metric spaces is just usual shifted. This is a consequence of the fact that not only of the fact, but also needs the fact that discrete metric spaces form a co-reflective full subcategory of metric spaces called standard products. this shows that everything shifted over sets is shifted over metric spaces. And this is clearly correflective because the correflection is that you have a metric space and you take a discrete space and you take a metric from discrete to this space. But discrete metric spaces don't form an enriched correflective subcategory. So metric spaces might contain adjuvated colimits commuting with finite products. You see, conical colimits commuting with finite products or metric spaces are just shifted. But they might be adjuvated colimits which commute with finite products. I don't know. Which in fact happens in posets. So now the situation in posets is that, so at first, again, also in posets, the usual shifted colimits commute in posets with finite products. But there are some weighted colimits which commute with finite products on posets, and these are reflexive coinserters. I will not give the definition of that, but they might give you intuition for this. This was in John's paper. It's from John's thesis, yes, this fact. And now every finite poset, now I will give you intuition for that. Every finite poset can be obtained from finite discrete posets by means of reflexive coinserters. So how you do it, yes, that you take finite poset, maybe you take finite poset, maybe just let me do. You have finite poset. Now you make it discrete like an anti-chain, and now you have a finite poset. You take its elements, and now you take the order relation here. And you get two maps giving, say, if you have x small equal to y, so it's that this 2x and 2y. And now the reflexive coinserter, in fact, it gives you the given poset, because just it takes those points and puts this order to them. This is how this construction works. Yeah, so that's coming back. So every finite poset can be obtained from finite discrete posets by means of reflexive coinserters, and the home functors of finite discrete posets reserve reflexive coinserters. So again, this reduction argument, which I showed to it, lemma 1, shows that enriched monads given by enriched finite recreational series over posets, where yi operation has x discrete, they preserve not only filtered colimits but also reflexive coinserters. And the paper of Adam and Dostan Velebil from last year, they showed conversely that any such monad, this filtered colimits and free coinserters, that any such monad is in fact given by set theory. This doesn't immediately follow from things, because this kind of reduction, which is easy to do it for filtered colimits, is not so easy to do for reflexive coinserters. But this can be also shown using XY operations. By the way, all what I'm telling you is in my archive paper, which just today the updated version appeared, and this argument how one can show it using XY operations if it's contained there. But also let me to add another thing here, because what happens, so this monads finitely preserving reflexive coinserters are those where x, y are finite, but this is discrete. What happens if you make both x and y discrete? So you see, do you remember when I mentioned this paper of power? So I told that enriched monads preserving filtered colimits are given by enriched Lobby theories, which means that you, as arities, you take finitely presentable objects. But the same mechanism also works not only in, say, doctrine of finite limits, but in doctrine of finite products, that you have, if your category is not locally finitely presentable, but locally strongly finitely presentable, I will tell you what does it mean. For instance, this is the case of, so just to change the definition of locally finitely presentable. So instead of finitely presentable objects, you take those perfectly presentable objects. So it means that the home functor preserves shifted colimits. And then the other part of the definition that any object is filtered colimit of finitely presentable. So any object is shifted colimits of those shifted finitely presentables of those finitely presentables. And of course, the category of poset is not strongly finitely presentable because what if you take finite discrete and you take their filtered colimits, you get still discrete. If you finite discrete and you take reflexive co-equalizer, you still take discrete. So you cannot leave this discrete by these things. So which means that it's not true that any poset is shifted colimit of discrete. That's not true. So, but in the enriched setting, it is true. Because any poset is really a shifted colimit of discrete, because you can take reflexive co-equalizer to put order there. So in fact, the category of poset is strongly presentable as a closed category. And then you have the same machinery as this power. By the way, this machinery is in my joint paper with Steve Lack, that's explicit there, that such monads are precisely those where arities, where you use cotensors, and arities are perfectly presentable, which means discrete, and a cotensor is reduced to products. So by this thing, you can get that if you add to this Adame-Gustav reliable result, that this monads preserves shifted colimits and reflexive co-inserters, which means that pre-shifted, it preserves enriched shifted colimits, then such monads exactly corresponds to those given by XY array operations where arities X and Y are discrete. But still that's some order present here. For instance, take as unit operation, so X and Y is 1. So then this operation should be monotone. So order is present in this definition here, but arities are discrete. Yes, so this is the Swiss poset. So now let's now come to other category, complete metric spaces, which is again local everyone presentable as a closed category. And then unit ball function is monadic. The corresponding monad now preserves the colimits, but this category is not isometric locally finitely generated, because in metric spaces, finite spaces are finitely generated isometric, but not complete metric spaces. So if you pass from metric to complete metric, so you made this monad preserve direct colimits, which is not true over metric, because how you make direct colimits of complete metric? You take direct colimits of metric and complete. It doesn't influence it only one directly, because then this just followed, this completion is followed by that. So the category of Banach spaces is symmetric monoidal closed, but now with projective tensor product, which basically is given by this condition. And now Banach spaces are isometric locally finitely presentable, where finite dimensional Banach spaces are finitely generated. Yes, this is in my paper with Adamek I talked about at the seminar last year. You see this finite metric spaces works well. this finite in probability spaces doesn't work, but on Banach spaces it works well again, because you have also plus which changes situation there. So this category Banach spaces could be also a good base category on which this theory can be applied, because it's isometric open and presentable as a closed category. And for instance, as an example, then you can take Banach algebras or unital Banach algebras, which are monadic or Banach spaces. The point is now that here you have this crucial property which is defining Banach algebras is this one, and this has norms small equal to 1 because this tensor property is different now. Yes, over metric spaces you could do this plus, and you got this thing for plus, and now if you're going for multiplication, so you can do it over Banach spaces. And the same is true for inverted Banach algebras. But if you have unital C-star algebras, which are inverted Banach algebras satisfying this condition in norms, so the forgetful factor has left adjoint, but I don't know that it's monadic. I would like to know it. Yes, I would like to know, but this is not equational condition. So that's the question here, and that's all what I wanted to tell you. Yes. Thank you.
Okay, thanks very much for the nice talk, and we can give our usual round of applause, silent or otherwise. So. And so if anyone has any questions, feel free to unmute yourself and go ahead and ask one.
Well, I have a comment rather than a question. Do you hear me?
Yes, yes.
So you mentioned 2 papers where I am a co-author, in which somehow you indicated follow from your approach. And this is a discussion we have had before, and I would like to continue this discussion that I don't agree. So I think there is a big difference between a categorist equational theory and between a universal algebraist equational presentation. And they are definitely related, and they are definitely not equal. And I think the best way how to say more about this would be to offer a seminar talk. John, what would you say to a talk about monads on the category of posets? I have essentially 3 things to say in case you are interested. 2 are in 2 different papers, and the 3rd one is completely new, characterizes enriched monads that preserve epimorphisms in a way that is completely analogous to the Mardare, Plotkin, Parangaden theory as Jirka mentioned it. So, by the way, I started completely wrong. The right start of my discussion was that I really like what Jirka is doing, and I think it's really putting completely new light that I didn't see before. And only then I should have said, comma, but it's not exactly the same thing that we've been doing, and I will try to present more, and then you can judge for yourself. For yourselves, I mean. And if I may continue, just one little technical thing. Jirka mentioned finite products in metric spaces, that they might commute with other types of of colimits and that it's an interesting thing. So I definitely proved that they do not commute with epsilon co-inserters. Epsilon co-equalizers. An epsilon co-equalizer is a mapping that if you take the two compositions, they have a distance epsilon and it's universal among those. So finite products do not commute with reflexive epsilon co-equalizers in metric spaces, unfortunately. That would make algebraic life there easier, but that's simply untrue.
Well, we have a spot in March. I'll send you an email about the talk, perhaps, if you're interested, Jukka.
Yes, certainly, but just let me just a small reaction to your comment to explain. Yes? So the monads are just the same, monads preserving that and that and that. And now they are, of course, this equation representation I presented is not identical with that you are using here. But just one can translate one to the other and back, I believe. If not, of course, so then that's something wrong in things I wrote, yes. So I never said that this is the same thing, but it's how to say one can translate it from one thing to the other one. So certainly it would be interesting to talk about this translation, how one formalizes, say, equation theory in various languages.
Okay.
I have a question or comment exactly on this, if I may. So first of all, thanks for the very nice presentation, Jukka. And then my question or comment is on the way the inequations appear in the POSET example. If you could go back to that slide.
Yes, yes.
And this, I think this alludes to the question how these translation between the different notions of theories would work. Yes, this one. So the way inequations are expressed here, the way I understand this is essentially saying the elements of these x, 2 array operations, they are not really inequations, but they are pairs of operation symbols of operations which are related by an inequality relation. So that, if that's correct, that would mean in order to encode the presentations of theories that we have in the paper, what you would do is would say, okay, the operations are x, 1 operations, and then inequations in our sense are pairs of terms over these operations, which are specified related by an inequation. So in order to express this here, you would have to say, okay, I take two operations which correspond to the terms that I want to put on the left and right side of my inequation. Let's call them f and g, because that's how they're called here. You put them in x, 2 and say, so f is less than or equal g, but then you also have to add equations which say these operation symbols f and g, they correspond or they are equal to terms I form over my actual operations, which I use to specify my theory. And I think that will be the translation in one direction. In the other direction, I'm not sure now. But I think this is essentially the difference. So here, and I think it's the same in what John Power did, and I don't know Burke's and Garner's paper, but so what happens is that inequations are encoded in arities of operations. So if you want to translate the usual inequation representations of ordered algebra, you have to add equations. Yeah, it's a syntactic difference. And then one can argue what's nearer to the practice in ordered universal algebra.
Yes, so if I understood well, so you say that one can have a different presentation of equational theory, which have equivalent semantics, but say, syntactically they are not the same, but they are, we can translate one to the other. Do I understand it well?
Yes, so this is one thing. So, but or let's maybe in other direction. So the role that inequations play here is a different one than equations, right? So because in your definition you had operations and you had equations, and these equations were pairs of terms.
Yeah.
So what one would like to see is that inequations are also pairs of terms. But what happens here is that they are essentially, the inequations are hidden in the arities.
Yes.
And I think this is the difference.
Yes. Yes, so I just think about this because I would like to understand the reason that, yes, to the difference between these two possible formalizations. Yes, thank you for this comment.
Right. Okay. Yes, and thanks for the very nice presentation once again.
If I may, I wanted to make just one small comment. So my point of view on this story is like from the enriched point of view. So I don't have a strong attachment on which category we enrich. And as I was mentioning to Jiří in one email between us, I think another good example that one might look at is given by the fact that compact spaces are finitely generated with respect to closed embeddings in topological spaces. So there are many finitely generated categories of spaces with respect to closed embeddings that one could look at. And so studying monads there would give something, sorry, compact outgrowth, I mean, my fault, compact outgrowth. So there are many monads that one could study of topological nature that in some cases, I think all of them, because you always study finite stuff here, would generalize this treatment, I guess.
No, certainly there are, I think, many situations when one can look at, yes, because this, say, whole machinery of this John and Richard paper is very powerful, and it could be applied to many other situations. Certainly, this is one of those. And somewhat, Ivan and me added to that this aspect of locally generated things, yes. And this theory just can be adapted to that. And the other thing is that these possible reductions, how you express arities by some kind of polynomials of small arities, and what the effect on monads, yes, on both sides. So mostly manifested here on examples, but probably one can do it much more complete and by these more examples. Yes. So you are certainly right. Yes.
Okay, so I think a few people are having to leave soon for, so if there aren't any more questions, let's thank Jiří again for a very nice talk. So we can stop recording for today.